Hello everyone, my name is Swaraj and today I'm going to talk about this interesting topic called gradient descent with momentum. So what is gradient descent with momentum? It is an optimization algorithm that almost always works faster than the standard gradient descent algorithm. So let's say you are trying to train a linear regression model of the form yi is equals to wxi plus b, where w and b are the model parameters. You decided to use mini batch gradient descent as your optimization function. And the last function that you decided upon was, let's say, root mean square error loss function. The counter plot which you're seeing below is basically the counter plot for the loss function, the RMS loss function with respect to the parameters, and the red dot which you're seeing at the center is the global minima which we are trying to reach. So what a standard mini batch gradient descent would do is it will start with from any random position on this counter plot, and to decide on which direction one should move on, it will calculate the gradient over the first mini batch and use that direction to take a step on this contour plot. Now to decide where should we move next, it will calculate the gradient on the second mini batch, then move in that direction, the third mini batch and move in that direction, and so on, so forth, until it reaches closer and closer to our global minimum. Now you can see that there's a lot of noise in the path which mini batch gradient descent chose to reach the global minima. And this is because of two reasons. The first reason is that a counter plot is not subtler uh, in nature. And the second reason is that we are to decide in which direction we should move, we are using a mini batch to calculate the gradient and not the entire data to calculate the gradient. And what if I tell you there was a way to reduce our noise in the vertical direction and faster our learning process in the horizontal direction? Now this is exactly what gradient descent with momentum does. So instead of calculating the gradient on the current mini batch to decide on which direction we should move, it also uses the information from the previously calculated gradients. So let's say uh, you are on this position. Now what mini batch gradient descent will do is it will calculate the gradient over this mini batch, and it will suggest that we should move in this direction. So, but what gradient descent with momentum will do is it will not just use this gradient information, but will also use the gradient information of the previous iterations. So let's say it is using these two gradients. It will add all of these to decide on which direction one should move on. So as you can see, when we are adding the previous two gradients, the vertical component is kind of trying to cancel one another. So it is basically trying to reduce the noise in the vertical direction, and its horizontal component is trying to push us in a faster way towards a global minima. So what this will result in is in some vector of this form. So what this essentially is doing is so what gradient descent momentum is doing is it will give us some path similar to this one. So where noise in the vertical direction is reduced and we are requiring, few less steps to reach our global minimum. So what are the steps to perform gradient descent with momentum? Uh, so as we discussed on the previous slide, that to decide on which direction one should move on, we are not just using the current mini batch, the gradient calculated from the current mini batch, but we are also using the average of the previous gradients and using that average gradient to update our model parameters, or decide on which step one should take on that contour plot. So these two variables here, VDW and VDB. So what they're trying to do is they're trying to accumulate the average of the previous gradients, and this form of accumulation is called as the exponentially weighted moving averages accumulation. So so as you can see, this VDW will basically hold the average of previous, let's say, three gradients, and then we are using this VDW to update our model parameter, which uh, is basically same as deciding on which path or which direction we should move on from our current direction and that counter plot. So one interesting thing to note here is that this beta parameter here basically controls how many previous gradients we average over. So the total number of, so let's say you have decided of some beta like uh, zero point 0.9 for your training purposes. So the number of previous gradients that are using for averaging is 1 over 1 minus beta. Uh, so in this case, it will be 1 over 1 minus 0.9, which is equal to 10. So you will be averaging over the previous 10 gradients if you select beta as 0.9. So what are the pros and cons of gradient descent with momentum? So the first pro is it is always faster than the standard gradient descent algorithm. The second pro is it allows us to choose a larger value for our learning rate, which also helps in the faster conversion. So as we discussed on the previous slide, gradient descent with momentum tries to reduce the noise in unwanted direction, which also does helps us to allow us to select larger learning rate, uh, so that we don't move in unnecessary direction, but we are choosing a larger learning rate helps us move even faster in the direction which we need, which is the direction towards the global minimum. And one of the cons of gradient descent with momentum is, like, in some cases, might overshoot our global minima and just keep oscillating around a global minima. But we can, address this con by using another variant of gradient descent with momentum, which is called Nesterov accelerated gradient descent algorithm. So, thank you.